Simple proofs involving integers. Remember to look back at Chapter 2 for symbols and terminology we will use in this chapter. Closure laws. A set is closed under a given operation if the result of the operation on members of the set always belongs to the set. We'll see what that means in more detail as we do examples. Addition is a closed set under the integers because the sum of any two integers is always an integer. So the set we're considering here are the integers. Multiplication is a closed set because the product of any two integers is always an integer. However, division is not a closed set because the quotient of any two integers is not always an integer. For example, 1 divided by 2 is a half, which isn't an integer. In general, a set S is closed under a particular operation star, which may be something we're familiar with, such as plus or subtract or multiply or divide, or it could be something else we've defined. If and only if for all A and B in S, so A and B are two members of our set, which might be the integers, A star B, where star is this operation, is also in S. So S is closed under the operation star if and only if A star B also belongs to S. This symbol here means for all A and B belonging to the set S, where star is a two-number operation, for example, adding or subtracting, and so on. Consider the set of positive integers. Remember, that's the same as the natural numbers. A says, is the set closed under multiplication? Justify your answer. If we take A and B as positive integers, then AB would belong to the same set. If you multiply two positive integers, you get a positive integer as the answer. So yes, it's closed. Is the set closed under subtraction? The answer here is no, it isn't, and all we need is a counterexample. If we do 3 take away 5, that's equal to -2, and -2 does not belong to the set of positive integers. Prove by contraposition that 2 is the only even prime number. First of all, we know that 2 is prime. That's an important fact. Now, what we're being told here is to prove that if n is equal to 2m, so that's an even integer, where m is a positive integer, so if m is 2, this one is 4, if m is 3, this one is 6, and so on. With m greater than or equal to 2, so that's from 4 upwards, that means that n is not prime. So that's the original statement. The contrapositive of this, remember for contrapositive, we'll start with P implies Q, which is what we're trying to prove, and what we actually prove is that not Q implies not P. You may see other symbols for not, such as bars and dashes, or even tildes. Now, if this is statement Q, and we can't be talking about the integer 1 here because we're talking about even integers, then not Q is that n is prime. And then we want the opposite of this one, so not p, that must be n equals 2m. M is an integer, but m is equal to 1. N equals 2m has factors 1, 2, m, and 2m. So that's 4 at the very least. If m has multiple factors, we'll be able to split that further. So let's just put at least. But this is just 2 factors if m is equal to 1, because this one will become 1 and this one will become 2. And that does it. That's proven it. We've shown that n is prime means that this m has to be 1. And we can now do exercise 7.02 on page 249.